graded quotient. So let me remind you that my graded quotient like this. And here are of course rational number. But I put this condition. Why this condition? So we have this inertia group. Inertia group is the kernel of G to the action of residue field. And P is the inertia fixed part. P is the wide ramification group. So this is as so undefined. So this is nothing but lower number in filtration. I'm sorry? Either the residue field of the extension. Thank you. So we have inertia group and wide inertia group. And the fact is that, so I don't prove today, but G1 is inertia group, and G1 plus is P. So, so we will be interested in wide ramification. So we are interested in this part. And this condition corresponds to this one here. Okay. So we are going to study this graded quotient. Now, the goal of this second lecture is first, we want to show that so this is in fact abelian group. So we know that this is a P group, but in fact we know more than that. So first go G for R bigger than 1 is abelian. And the second part, second goal is that this is in fact FP vector space. In other words, this is killed by P. So we want to see that this is abelian and killed by P. So how we study this? So we already know that this construction is compatible with quotient. So by with quotient, so we may assume GR plus is 1. So we take quotient by this part, so we can assume this part. Then, so in this case, so of course this gray piece is just the last piece of filtration. Okay. So we want to study this graded quotient, or the last piece of filtration. Then the first non-trivial fact is the following. So let me assume R bigger than 1. And consequently, FR to FR plus, sorry. So let me remind you that, so this condition means that FL to FR plus L is a bijection. because this is FL divided by GR plus. So we assume this and this property. Okay, then so we have closed fiber of this normalization, geometric closed fiber of the normalization of the dilatation. From this to the just reduced closed fiber. So this is without normalization. This is normalization. So this is before normalization. And we take the reduced part. So reduced closed fiber was just dilatation, and here we have normalization. So because and after for K, and this is by reduced fiber theorem. This is we already know this is reduced. So both are reduced. So we are looking at a more finite. So and this is normalization. This is a finite Morrison reduced schemes over F bar. And the claim is that this is in fact finite term. And this one has a simple description. This part so this is just vector space over the residue field. Sorry, let me go back to F prime. So K prime is sufficiently large. And F prime is the residue field. Then, so this is just a base range of this. Okay. And this is mk prime r prime divided by mk prime r prime plus 1. And r prime is, let me remind that this we multiply the ramification index to make it integer. Home space from here to conormal sheaf field. Okay, so N is the conormal sheaf of the immersion. So this is a smooth over S, and this is just a ring of integers. So both are regular schemes. So this is regular immersion. So this is local. This is free OT module. Of finite length. And E is residue field. So this is F prime vector space, and this is E vector space, and this home is as F vector space. So altogether, so this is F tensor E prime module. And we regard this module as so this is so we regard this as a vector space over F prime, and this we regard this F prime as a scheme, and we get this. Sorry, I need to put the dual here. So the decision is may look complicated, but this is simply some vector space. So this is just vector space over the residue field. And we get finite eta covering of this vector space. That's the yes.
Excuse me, isn't this description for what's the bracket R?
Huh?
What is the definition of your difference between your bracket and your
Yeah,
could you remind?
Bracket is just dilatation, and round bracket is normalization.
Yes, but the description you gave
Yeah.
is for the one with the round bracket or
Yeah. Sorry. Yeah, that was a misprint. Thank you. Thank you. Yes.
and also you wrote E prime somewhere. F prime times E prime module. E prime doesn't appear, so it should be E.
Yes. Yeah, thank you. On this finite eta, I'm going to tell you how I get to. Yeah, I'm going to tell you how I see finite eta. And cotangent complex will come later. Okay, so sketchbook. So we start with Cartesian diagram. So this is as before, and so this is similar. So we just take smooth scheme of S, and we take immersion, and we have a Cartesian diagram, and we may assume that this is finite plot. So we can construct such a commutative diagram, such Cartesian diagram, and we start from here. Then, by applying the construction, we get this commutative diagram. But so this is a simple one. So this is smooth before taking normalization. So this is smooth over S prime. And so the vertical arrows are finite because we are just taking the normalization. So we get this diagram, and we look at the closed fiber here. And this is a split eta covering. And so this part is straightforward, and we look at this distribution from this. So the theorem says that this is eta on the closed fiber. So we want to show that this map is eta on the closed fiber. Then what are the assumption tells us? So assumption is that so this FL to FR plus L is bijection. And FR plus L is defined as the image of the so we have map from FL to fiber functor from here, and the image is that and FR plus L is its image. And from this description, this implies that QS, this motion, which we want to show that this is eta. So this is in fact eta on the image of FL. So we have a finite motion, and we look at the closed fiber, and we have image of FL. And we want to know that this map is eta on the image of the closed fiber, but we already know that this is eta on the image of these finite remaining points. And we want to extend the property to the whole closed fiber. So how we can do that? So to do that, so we apply Zariski-Nagata theorem. The purity. So to prove this, it suffices to show that the JX fiber is eternal. Is eternal on the neighborhood of on the neighborhood. So JX fiber JX fiber of a neighborhood of closed fiber. So this implies the same. So by Zariski-Nagata purity, if we know that the JX fiber of a neighborhood of this closed fiber is eternal, then we can conclude that it's eternal on the neighborhood of the closed fiber itself. And so this eternalness is a point of the proof, but this is rather delicate, so I can't prove that. I can tell you now how I prove this part, but so this is the idea of the proof, and the point is this eternalness. The JX fiber of a neighborhood of the closed fiber. Yeah. So the JX fiber is too big, but we are looking at a partial blow-up. So the neighborhood of the closed fiber gets smaller, and on this smaller part, we can prove this eternalness. Okay, so this is the first step. Now, so we have this eternal motion, QF prime R to QF prime reduced. So this is the finite eternal. by the cell I just erased. The next step is to make this construction. Factorial in L. So if we replace this f prime by f bar, then it doesn't depend on k prime. So this is good. But this still depends on q. So I want to eliminate this q. So to eliminate this, dependence on q. So this is our goal. So to attain this dependence, I need to focus on the case where dimension q is minimal. So in this case, so I just erased, but let me so just let me remind that this is so this reduced closed fiber has this description, and we have a dependence on q here. But under this assumption, we can make it canonical. So under this assumption, so this case, this conormal sheaf reduced is canonically identified with Thorne module of omega 1 over OK over E. So this is simply come from we have free resolution omega 1 T over S. Oh, this is nothing but this. Omega 1 Q over S tensor well, and then T over Q. So we have a free resolution. And this minimality means that the morphism here induces isomorphism if we tensor further to E. So we get isomorphism on tensor over E if we assume this minimality condition. And then the map here will be 0, so we get isomorphism here. So imposing this minimality, we get a canonical description of the closed fiber on the right hand side. And from this, we can conclude that the closed fiber of normalization also are independent of choice of Q. This implies UF prime reduced So this is also independent of, so essentially independent of Q, of minimal Q. So let me call this theta over sorry, L over K. And sorry, theta is for bracket. Sorry, I'm sorry. So this will be denoted phi, and theta is that one. So so this is for KF bracket R. And this so this is independent of Q. Of choices and factorial. Yeah. So in this way, we get a nice object. So now we look at Galois action. So so we have a Galois group. Yes. Yes. Thank you. Yeah, it's fairly confusing. Sorry. Yes. So now we have this Galois action. And also, we may assume that our K prime is also Galois group and Galois extension. And we have also this action. And to distinguish them, so let me call this geometric action. And this is arithmetic action. So by the factoriative of the construction, both groups act on this construction. And we use a factor that they are commutative to each other. So this commutativity is by the construction, but you can clearly see the commutativity out of that description. So by the minimality, we can replace this by that guy. Then we have action of so G prime acts on this part and G acts on this tensor product. So by this definition, the commutativity, you see explicitly the commutativity. Okay. So now we look at this mark more closely. So we have phi to theta. And we have a map from FL. So this is the set of motions. And also here we have action of G and G prime here. And also the action is compatible with this. Now, let me state one lemma. And the proof will I give later. So that the proof of this lemma will use the cotangent complex. So the action of this, we take this subgroup. So this is P prime. And this is the inertia. So this is the subgroup of G prime. G. So we have this whole group, but we express the action to this subgroup. So for P prime on this first factor and wide inertia for the first factor and usual inertia on the second factor. on this target is trivial. And out of this description, the triviality here is trivial. But the triviality there is not so trivial. So here we use cotangent complex. So this we will see later. Okay, so to go further, we fix one embedding. So we regard L as a subfield of K prime. Then using so fixing this, so we fix one point in FL. So this the image of this point defines a point in phi and also on theta. And so now we focus on the connected component containing the image. So connected component containing the image of the point. The point means this fixed embedding. And the connected component, I put a small circle here to indicate connected component. Now, so before taking the connected component, so we look at the most over F, but by fixing this, so this is a vector space over F prime. The same, but and so yeah. To be precise, let me. So 1 OL omega 1 F prime. So we have such a description. And let's take the origin. The origin is in fact this image of the point we chose. Now we have fibers. And this fiber is in fact GR torsion. And we already know that this is finite et al. So this is finite ether and the fiber is GR tosa. And we have natural action restricted to disconnected component. And from this, so this is itself, so the fiber and also the whole space is GR tosa. And they are connected. So this means that we have isomorphism. So we have finite ether Galar covering. So we have decision of the Galar group. So this comes from this geometric action. And also we have asymmetric action. So we have map from asymmetric action. And in fact, this is also surjection. So this comes from this. So fiber here. This comes from the fact that this fiber here is the intersection of this is identified with if we under the disconnected component. Using this description, we see this surjectivity. And so this implies the first result. So proposition GR is commutative. So we have two actions of these two groups. And one is isomorphism and one is surjection. But we know that they are commutative to each other. So they must be, this must be abelian. So the first goal is attained in this way. And this description, this construction gives us more. So we have this finite covering, finite ether covering, and this is in fact GR tosa. So this defines element of H1. So simply because this is GR tosa. Now we know that this is abelian. This target has a description like this from GR dual to H1 theta 0 over QP divided by Z. And let me remind you that this is a P group, and we know that this is abelian, so this cohomology is identified with this group. So we can regard this as a homomorphism like this. And we regard this cohomology class as a homomorphism, then this homomorphism is in fact injection. So in this way, we get to so as a byproduct of this construction, we get the injection like this. And we will going to use this property, this injection, to prove that the second goal today, which is that this is now the second goal is let me remind that this is a FP vector space. So we use this injection to prove this property. Yes. Sorry.
Can you explain a little bit about why the map on slide is?
This is subject. This is subject. You look at what is this intersection. Then the subjectivity is another immediate from this intersection. This in the description of intersection, but I'm sorry that I don't have. I don't have time to do this. So maybe I will tell you later. But to go further, I need to use cotangent complex. So cotangent, let me recall that cotangent complex is defined for most of schemes. And then cotangent complex. So this is a complex of OX modules. And homology sheaves are quasi-coherent. And 0 and this positive. And H0 is omega 1. H low 1. Yeah, and if X smooth, then omega 1. This is the quasi-Ising. So cotangent complex is some sort of generalization of omega 1. And if X is X to Y is immersion, so in this case, omega 1 is 0, so you have to start from the first one. So in this case, H1 is a conormal one. And similarly, if this immersion is a regular immersion, then we have this map is a quasi-isolation. Okay, and one more general property is that if you have two morphisms, then we have a distinct triangle. So in this case, for omega 1, we have just a right exact sequence, but short exact sequence, but with these cotangent complexes, we have distinguished from. So we use such general construction. So first we apply this to the immersion, like this. Then, and we apply this to this distinguished triangle to our case. Then the first one is just so you take. And here omega 1. The first motion is smooth, so you can forget the derived thing, and this is just tensor product. Then we have cotangent complex of T over S. And the map here is a regular immersion, so we can apply this one. So we get such distinct triangle. So from this, we see that. So we know that. So as we have already used that, we have a resolution. So this resolution tells us that this L2 over S is omega 1 T over S. Put on 0. Okay, now we apply the same distinct triangle to this motion. Then so we have to worry about this derived thing. L over S to N. Like this. Then what this gives us? So we start from 1 here. So we already know that this is omega 1. So we get a tensor product. So we start from tau 1. And we get something here. The next one is N2 over Q tensor OL E and omega 1 OL over okay, maybe. Okay. And H0. L over S. Okay. So here the point is that the injectivity here. So I postpone the lemma. So what was the lemma? So the lemma was that so G1 acting on O1 is trivial. So we want to show that the action of inertia on this total one is trivial. So G1 acts on the residue field trivially, but the action may not be trivial here. But this lemma says that the action on tau is trivial. So this is not so clear, but once you get injection here, then here this G acts through E, so the action is trivial. I have 5 more minutes. 10 minutes. Okay. Yeah, thank you. Okay, I can use nicely this H1. So this H1 will be important for us tomorrow. So let me study this H1 a little bit more. So to study H1, so we look at more smooth like this. So this one I should write the spec. Okay, so we apply this distinct triangle to this case. Then this start from E tensor F n F over S shifted Y1 goes to what we want to know, and something a little bit easier. So we get a distinct triangle like this. Okay, now, yeah, so we need to know what is this. So to know what is this, so we study this first. So to study this, we replace this S by spec of Fp. Then similarly, L. So this is not quite smooth, but because this may not be finite type, but it's a limit of something finite type. So we can take the limit. The construction of cotangent space is cotangent complex is commute with inductive limit. So this gives distinct triangle like this. Sorry, I don't.
The last one.
Yeah. NTQ is conormal. You mean this one? Yeah, it is oil. Next, this one? Yeah, thank you. Like, give me this. Yeah, thank you. Okay. So combining these two together, yeah. So we start from here. So E tensor. So this NF over S is just this heuristic tangent space. Yeah. And then now we get to H1. And the next one is this. But this H1 with this is just a kernel of this one. Yeah. And the kernel of this one is just omega 1. So we get this exact sequence. And if so this will be 0 if E contains this pair in several extension. So in this case we get so this mysterious vector E vector space is extension of this heuristic tangent space by the color extension of this one. So in this sense, this is some replacement. Replacement of the cotangent space. So this is the cotangent space of the closure point, but the discrete variation link has dimension 1 larger. So I need one more parameter. This gives the required extension. So let me stop here today, and we continue the study of graded quotient tomorrow. Thank you.